me introduce you to Professor Walter Chapman. He is currently the William Akers Chair Professor, Director of the Energy and Environmental Systems Institute, and the Associate Dean for Energy Research at Rice University in Texas. Professor Chapman has an interest on the development of statistical mechanics-based molecular theories to study structural property relations in complex fluids. Among his contributions, he is famous for the development of the SAFT equation of state. He has more than 290 publications with more than 12,000 citations. So, Thiago, are you going to show that second slide? Okay. So this is a history photo of Professor Chapman and Professor Papa from our laboratory.
It's the fase 2002, I think.
Exactly.
I don't know if Professor Papa is here, but that's an interesting picture we would like to share.
We haven't changed.
A little bit.
A little bit.
So I think we can.
So thank you in advance, Professor Chapman, and we are here again to learn from you.
Thank you, Professor.
Great. So thank you so much for the invitation. And I think it's a great initiative. I think there's a great opportunity for us all to share information. First, I didn't mention on Monday. This is the main quadrangle at Rice University. It's a beautiful campus, and I hope all of you have the opportunity to come to Houston and visit Rice sometime. The weather's always 75 degrees, 23 degrees Celsius, and sunny, and dry weather. But that's not true. But anyway, so I'm going to talk about thermodynamic modeling of fluid distribution and phase behavior in nanoporous shale. What we're developing has application to a wider range of systems, any sort of nanoporous type of material. The application here is mainly in oil and gas, but as I said, we can apply this in other areas. So why are we interested in shale? Really, George Mitchell, who was born in Galveston, Texas, and made his fortune in the energy industry, introduced the idea that we could produce oil and gas from tight formations that we talk about shale oil and shale gas. These are just very low permeability formations. And he spent a small fortune figuring out how we could do this. And it really changes the world. And we've already seen that. The reason we're in an oil price war now is that Saudi Arabia and particularly Russia see the shift in the ability to produce energy. You all probably know that if Argentina develops their shale formation, they'll be one of the top 5 producers of natural gas in the world. So it really changes the landscape. Companies are even looking at building polymer plants in the United States again because natural gas is so cheap. Just less than 10 years ago, the United States was building liquefied natural gas import facilities because the United States did not have enough natural gas. Now natural gas is so cheap, we have a hard time giving it away. So there's a rapid increase in production that's been allowed. The challenges, the formations have very low permeability, low recovery factor. There's complicated thermodynamics and transport properties in this reservoir fluid. And let's see if I can find there. And there's different compositional and physical properties of each reservoir. So this needs to be understood. This is production history. You can see here from 2011, the natural gas production has become dominated, at least in the United States, by shale gas. And so it's become a very important source of energy. What this slide describes is the, and I won't go through this, but it's as organic matter called kerogen decomposes depending on the environment. If it's a lake environment, it's an oil-prone shale. Marine environment, you produce both oil and gas. And terrestrial land is more gas-prone. And what happens is, this is the hydrogen-carbon ratio, and this is the, I believe it's oil to carbon. But as you go from immature to mature, it goes through various chemical transformations based on temperature and potentially iron and other components in the soil. And what happens is you produce a cross-linked network of polyaromatics, and that's what this kerogen is. We consider it to be a source rock, but now we're producing actually oil and gas that's not migrated to a trap, but is essentially remained in place. But although there's people have proposed force fields to describe the kerogen, which is what these little diagrams are supposed to be. These are basically polynuclear aromatic cross-linked molecules. There's been no molecular model or molecular theory proposed for the kerogen. And so I'm going to talk about that in this talk. So what we're interested in is describing how fluids partition between the macropores or fractures, which is the bulk phase, the nanopores, and the organic matrix, which is the kerogen itself. And so these are some micrographs that people have taken showing what the kerogen looks like from the macropores, and as you go to a smaller and smaller scale, see B here is blown up to this. You find pores that are on the order of a couple of nanometers. And so we need to understand how fluid distributes between the macropores, the absorbed in the kerogen itself, as well as these nanopores. And so we're involved in a project where we're using a combination of nuclear magnetic resonance, molecular dynamics, and then a theoretical model to understand the partitioning as well as the dynamics of movability, let's say, of fluids in the kerogen. So with NMR, we're studying fluid relaxation, fluid distribution, and diffusivity. With molecular dynamics, we're using molecular dynamics for the first time to interpret relaxation behavior with NMR. We're calculating fluid distribution and transport properties, and it provides a validation for the theoretical model where we're describing fluid distribution, mixture behavior, as well as estimation of fluid reserves in these kerogen phases and in the shale formations. The approach we're taking is we're using the statistical associating fluid theory, SAFT. SAFT is, I proposed and developed SAFT in my PhD thesis work, and as well as work that my first several students did at Rice University, validating the equation of state. The idea is that we start with it's a perturbation theory. So we start with a reference fluid, in case maybe a hard sphere reference fluid. We then put little bonding sites on these spheres and calculate the change in free energy due to either association or, in this case, chain formation. And then we include the interaction between the segments and we can actually, the molecules themselves can hydrogen bond further. For this talk, I'm going to really talk about the just chain formation and the dispersion. Not going to worry about the hydrogen bonding interactions. For non-associating fluids, the parameters are the number of beads that make up a segment, or number of segments, rather, spherical segments that make up a molecule. I need to know the segment diameter and the van der Waals attraction or London dispersion interaction between these segments. We're going to fit parameters to experimental vapor pressures and saturated liquid densities. And applications, of course, range a wide range of systems. I'll be talking about crude oil, asphaltenes. We've also applied this to gas hydrates, polymers, amphiphiles, alcohols, and so forth. So that was the bulk SAFT. What we're going to do is develop a density functional theory. We're interested in how molecules distribute with reference to a surface, for example. And to do that, to actually understand the structure of the fluid, we need to develop a density functional theory. But we take the same approach we did before. We'll start with individual segments and a density functional theory for spherical molecules. And we'll do a perturbation on that to develop a density functional theory for polyatomic molecules. This actually I proposed in my thesis work as well. And this is now used to describe structures of polymers. So in this case, instead of writing down the free energy, we're writing down a free energy functional because it's a function of the density distribution. There's a ideal gas contribution, the hard sphere contribution, and the ideal gas contribution is known exactly. The hard sphere contribution, we can use density functional theories that have been developed before, either due to Pedro Tarazona or Yuri Rosenfeld. Most people use the Rosenfeld approach, and that's what we're going to use. It's called fundamental measure theory. But then we need to develop the free energy functional for association or chain formation. I wrote down the free energy functional for association in my thesis, and in my own notation, this is what it looks like. We take the limit that we have total bonding, and it's the limit that these loci, which is the fraction of sites that are not bonded, goes to 0. You have to be careful because you have a log of this, and so that causes this, of course, would blow up. So we have to be careful how we take this limit. But in fact, what this term does is it enforces stoichiometry in our molecules. We end up with a free energy functional due to chain formation. This is approximate. We have a more rigorous result in this work by Jane from 2007. And this allows us then to describe inhomogeneous fluids. In a density functional theory, the way that's done is that you write down a free energy functional. This is a grand potential because we're going to set the bulk chemical potential. So the grand potential is the free energy that should be minimized when chemical potential, volume, and temperature are fixed. It's written as the Helmholtz free energy functional, a contribution due to an external field. And this is the bulk chemical potential, which is set. The free energy, the grand potential, is minimized with respect to variation in the density. And it ends up being just what you'd expect. It looks like just thermodynamics. The bulk chemical potential should be equal to the chemical potential of the molecule in the inhomogeneous system, and that's what's the case. This is the local ideal gas contribution. This is the local excess contribution, and this is the contribution to the external field. So here we show molecules between, say, graphite slits, and we can describe, this is the steel type potential describing this type of system. Now what's I find interesting is in the density functional theory, not only is it that the molecule, the chemical potential of the molecule is the same throughout the system, but the chemical potential of each individual segment will be constant across this system. So, and this is particularly important when we're dealing with surfactants or amphiphiles. So this is, in some ways, the way we're going to go through this. I'll talk about graphite nanoslit pores. We're going to talk about kerogen matrix model, and then the kerogen pore model as we go through this. For fluid structure and graphite nanopores, we use our density functional theory. We compare with our own molecular simulation results. This is methane in a graphite nanopore. Let's see, it's 3 nanometers in diameter. The temperature is 328 Kelvin. The points are molecular simulation results, and the curves are predictions from the density functional theory. And so this shows us really that fundamental measure theory works very well. Here we have ethane in again, a 3 nanometer pore, and then heptane in a 5 nanometer pore. All the molecular simulation results are ours. And you can see that the density functional theory does really an excellent job of describing the structure. There is some deviation here, and that occurs because the spacing between segments in our SAFT model is different from the spacing between, say, united atom segments in a trapped force field. And so you can see that although we're describing accurately in comparison with the molecular simulation, the average adsorption, there is a bit of deviation in the structure, but that's something that we believe we can live with. So these are graphite nanopores. We can also look at adsorption of CO2. Again, this is the average adsorption of CO2, ethane, and methane, again in 3 nanometer and 5 nanometer pores at 2 different temperatures. And what so what we're finding is that the theory agrees very well for the density of in the pore of these different components compared with pressure. There's results here from, I guess it's Gu et al. For the excess adsorbed amount of CO2 in a 1.5 nanometer pore. And you see interesting behavior at, as we change the temperature of the system, at lower temperatures, you actually see a maximum in the excess adsorption. And at higher temperatures, you see more just a smooth description of this. These are, this is a really nice result. It's excess adsorption, so it's excess to the bulk density. And so the agreement is actually quite good. We can then ask what happens for competitive adsorption, for example, carbon dioxide and methane in these graphite pores. And you can see here the carbon dioxide selectivity versus pressure in a 1.5 nanometer pore. Temperature is increasing as we move, as the curves move down. And you can see that the selectivity can actually be really high, where CO2 preferentially adsorbs in the pore compared to methane. And the reason we're interested in this is because there's interest in using carbon dioxide as to drive methane off the nanopores in the kerogen. In a similar way, in what's called cold bed methane, you're doing exactly this. You are pumping CO2 into methane seams, and because of the preferential adsorption, the methane is driven off the graphite, or in that case, the coal. Now, graphite's not necessarily the best model for all of this. But well, here's an example. I guess this is my last example. Here for Eagle Ford Shale or Appalachian Shale, you can see this is the distribution of gaseous components, mainly methane, but 25% other components. Appalachian Shale is 80% or nearly 80% methane and other components. And what we're showing are CO2 selectivities for all the different molecules in these sorts of pores. That's fine, and most of the work that's been done to study fluids in shale has looked at adsorption on graphite. But graphite is not really the model that we should be using to describe this. But what we're doing is we're validating our density functional theory through this. We're showing that the adsorption isotherms and phase transitions are well reproduced. We have selective adsorption of typically the heavier alkanes adsorb more strongly. And we're showing a reasonable prediction of CO2 selectivity. We've also looked at what happens if you have water in this, and it's interesting that you can actually increase the selectivity when water is present. We've also looked at ethane in these shale gas mixtures. This actually shows a phase diagram in comparison with molecular simulations, where we're showing the outer curve is the bulk phase behavior. The inner curves show the phase boundaries in these confined systems. You do see a shift in the critical point, and I could show you that, but we get good agreement with molecular simulation results showing how the critical point shifts. So instead, we're interested in developing a model that more accurately describes the kerogen. And the way people characterize kerogen is they look at solvent swelling in kerogen. Now, kerogen, again, remember, it starts off immature, and its characteristics change depending on the extent of diagenesis or metagenesis and catagenesis that's occurred. And so it's going to be important to have a model that reproduces what's happening. So what people do experimentally is they use different solvents and study the swelling of kerogen to try to characterize the kerogen or develop some sort of solubility parameter for the kerogen. So kerogen, again, looks something like this. And these are polynuclear aromatics. They are cross-linked, and as the kerogen matures, you get more and more cross-linking of these polynuclear aromatics. Alkyl groups are typically stripped off of these, and so it begins to look more and more like a system that we know already, and that's what's called asphaltenes. And if you look at the compositional analysis of kerogen, it's actually very similar to asphaltenes. And these are diagrams of what asphaltenes might look like. So I'm gonna change gears, and we're gonna look at asphaltenes for just a minute. So I can explain where that model comes from. So asphaltenes are an issue with flow assurance in the energy industry, particularly offshore, where you have pipelines running offshore, and you could have subsea completions with long, subsea completions, manifolds, and long tiebacks to platforms. Imagine that you get a plug in any of these flow lines, and this is a huge problem. These are asphaltenes on electronic submersible pump. This is a tarry type substance, but asphaltene can be tarry or can be very almost solid-like, and it can plug your tubulars. It's very expensive. If you imagine if you plug any of these lines, replacing the line is incredibly expensive. And so companies want to either avoid them or understand how they can inhibit the deposition of asphaltenes. The first thing to understand is when will asphaltenes precipitate? So in crude oil, there are different components. There are saturates, there are aromatics, resins, and then asphaltenes. And here, this is plotted versus solubility parameter. And so you can see that the asphaltenes are the most polarizable and highest molecular weight as well of the components in the crude oil. They're studied, and they're really, it's really a distribution of molecules. Here are cartoons showing what asphaltenes might look like. They're known to be insoluble in low molecular weight alkanes, and they're soluble in things, components like toluene or benzene. Now, I worked for Shell, and one of the first things I learned working for Shell is that that the less you know about something, and the less you could possibly know about something in the energy industry, the stronger the opinions. And so it's you can imagine that for asphaltenes, there's so little known that opinions are incredibly strong. And so it's a very combative, controversial field, but it rarely results in physical violence. However, there was one conference, I understand, where one of the speakers literally took a pair of scissors and attacked the view graph or transparency of another speaker. In fact, it was this diagram of an asphaltene. The fellow was claiming that no, asphaltenes have to look like this. They can't have these little alkyl chains. And so he literally cut up the view graph to cut these into smaller asphaltene fragments. So as a joke. What do asphaltenes look like in solution? At very low concentration, the asphaltenes tend to aggregate as what are called nano aggregates. And so these might be 3, 4, 5 asphaltenes that come together and stack. It's thought to be due to pi-pi interactions, but they don't grow any farther than that. And this occurs at part per million concentrations. These stay, at least the evidence seems to be that these stay about 2 to 3 nanometers in size until they phase separate. When they phase separate, we may form particles that are on the order of 350 nanometers in size. And then these particles tend to flocculate, and then we can start visually observing these. Because this happens at such a small scale, there's a lot of mythology related to asphaltenes, a lot of misunderstandings. And so the models that were used to study asphaltene phase behavior were very complicated. As it turns out, there's far simpler descriptions can be used. So when we look at crude oil, we can break it into gaseous components like methane, nitrogen, CO2, light alkanes, and then distribute the oil into what are called saturates, aromatics and resins, as well as these asphaltene components. And so what we did was we just said, you know, we'll just lump all the saturates together and get an average molecular weight. We'll lump all these aromatics and resins. They're both aromatics. The resins can be polynuclear aromatics, and we can put together the molecular weight of that component. And then we have this asphaltene component. The advantage of doing that is we actually have correlations of alkanes or aromatics with respect to molecular weight. Some of this data was some of these parameters. For example, here with PC SAFT, some of the parameters are fit by Joachim Gross. For example, for the normal alkanes, you can see the chain length is a simple linear function of molecular weight or carbon number. For the polynuclear aromatics, you get a nice correlation. And then as you add alkyl groups to the polynuclear aromatics, like here the alkyl benzenes, you see that you get a nice correlation of what's occurring here for the chain length. Similarly, for the dispersion energy or the van der Waals attraction between segments, for the normal alkanes, this reaches the limiting value, but you see with the other families, you see other similar correlations. What this allows us to do is if we know the molecular weight of the saturates component, we'll simply use the alkanes. If we know the molecular weight of the aromatic component, we know we're in the range between a polynuclear aromatic and an alkyl benzene. And so we have a parameter called the aromaticity, which describes how aromatic these components are. By fitting those parameters, we can then describe the properties of the asphaltenes. That's what was done here for certain crude oil. There's a group that measured in the laboratory as they added an alkane precipitant, what was the volume fraction of alkane they needed to add to the oil in order to precipitate the asphaltene. That's not exactly what they did. They took the oil, because the oil was opaque, so they took the oil, they added 50% alpha methyl naphthalene solvent to the oil, and so it's 50% alpha methyl naphthalene, 50% oil. Combine those two together, and then they added, say, heptane, and found out what the volume fraction of heptane would be needed to precipitate asphaltenes. They did the same thing with each of these normal alkanes. We then fit the SAFT parameters for the asphaltene to reproduce this curve, and we do so very nicely. Remember, this was done in a laboratory at room temperature. We then use that information to predict when asphaltenes would precipitate at reservoir conditions. And this is what we found. The points were measured by one of my students in the D.B. Robinson laboratory that doesn't exist anymore, but when the D.B. Robinson laboratory in Edmonton. And this is at reservoir conditions, 71 degrees Celsius, with different separator gas added back to the oil. In the oil industry, you describe separator, or you describe gas composition by gas-oil ratio. So these are two different amounts of gas in the oil. And so you can see that just based on the laboratory titrations, we're able to predict the asphaltene onset condition pressure, and you can see that we're up to 6,000 to 10,000 psi pressure. To do laboratory measurements, we can predict what's happening in the reservoir. Now, it's interesting, before we had done these measurements, an engineer from Shell told us that asphaltenes deposit in his wells over a range of pressures. That if the pressure is high enough, no asphaltenes will precipitate or deposit. If the pressure is low enough, no asphaltenes will deposit. But so as he's pumping off a well, he has to hold his breath, because he knows in a certain pressure range the well might plug. So you have to understand that. So why is that occurring? At high pressure, the oil is compressed. It becomes a good solvent for the asphaltenes. You can think of the solubility parameter of the oil is very high. As you reduce the pressure, what happens? The oil expands. The more gas that's in the oil, the more the oil will expand. As the oil expands, its solubility parameter is going down. At some point, the solubility parameter is low enough that the oil is no longer a good solvent for the asphaltenes. Asphaltenes begin to precipitate. As you continue to lower the pressure, asphaltenes continue to precipitate until you reach the bubble point curve. When you reach the bubble point curve, what happens? Gases start escaping from the oil. So as you reduce the pressure further, you're actually moving down the bubble point curve because gases are escaping from the oil. At a certain point, the asphaltenes become stable again. And so, in fact, what this engineer from the field told us was exactly right. It's borne out by the thermodynamics. At high pressure, asphaltenes can be stable. At low pressure, asphaltenes can be stable. There's an envelope of pressures during which asphaltenes can precipitate. If they precipitate, they can deposit. There are a number of things we've looked at for asphaltene stability. One is oil-based muds, another is gas injection, and third is commingling of oils. I won't show any results here. As it turns out, if you have oils from different reservoirs that you need to produce on a single platform, you're worried about whether the oils are compatible, because one could affect the asphaltene stability in the other. In fact, using the PC SAFT equation of state in our asphaltene model, there's a company has actually sold a field from the North Sea because they're going to have to combine oil from two different reservoirs to make a platform economic. And because SAFT showed that they're going to have asphaltene problems, and they also did experiments, I'm sure, but they sold the field. But let's talk about oil-based mud destabilizing as asphaltenes. Oil-based muds are made of olefins, and olefins, like alkanes, will destabilize asphaltenes. So there were some experiments done to understand how adding oil, and as you're drilling a well, you have oil-based mud. The oil-based mud will contaminate the reservoir. When you take a sample of oil from the reservoir, it's contaminated with oil-based mud. And so you're doing experiments on this oil to find out the asphaltene instability, and yet you need the information for oil that is not contaminated with oil-based mud. So the question was what you do. So it's understood oil-based mud should increase the asphaltene instability pressure. Here, the asphaltene instability pressure is 10,000 psi with no oil-based mud. They purposefully contaminated the oil, and so they expected the asphaltene instability pressure to increase. And that's what models showed. The asphaltene instability pressure would increase. What they found was actually the asphaltene instability pressure decreased. And so they wanted to understand why. We modeled this with our PC SAFT model, and we find, in fact, the asphaltene onset pressure should decrease as you add oil-based mud. And so the question is, why is that? And what we find is, as you add oil-based mud, you are diluting the gases in the oil. So your gas-oil ratio is decreasing. Because the gases in the oil are stronger precipitants for asphaltene than the oil-based mud, as you dilute these gaseous components, you're actually reducing the onset pressure. Why is that important? Again, when you have an oil sample you take to the laboratory, it's contaminated with oil-based mud. Through gas chromatographic analysis, they can see how much oil-based mud is present. And so now using this model allows them to digitally clean the oil. So you can go from a measured onset of, say, 7,000 psi in the laboratory to an estimated clean sample onset pressure of maybe 10,000 psi. This is incredibly important because it tells you how you should operate your field. We've also shown that PC SAFT can describe the effect of, say, injected gas. You might inject gas to pressurize the field, and it nicely describes how as you increase the amount of gas injected, it changes the onset pressure. And these are classic pressure temperature diagrams. At high pressure, again, you're stable asphaltenes. At decreased pressure, you're unstable. The cubic equation of state just doesn't do a good job of describing how the onset pressure changes. And this is why CalCEP changed their asphaltene model from cubic equation state to our PC SAFT model. Another interesting case is the composition of asphaltene as a function of depth. As you go deeper into a field, what you expect is the heavier components should tend to move to the bottom. And in fact, that's what happens. We're also interested in whether different layers of sand are coordinated, whether they're in communication. This well is clearly not in communication with these wells, because we can study how gravity should change the composition of the oil. Now, this is about at 8,000 feet. My student asked what would happen as you go deeper into the field. And what he found was, as you go deeper in the field, from around 8,000 feet to, say, 9,100 feet, there's actually a phase transition. Here we have nearly 58% asphaltene. And what's interesting, if you go to the logs, you find that, in fact, that's a tar mat is present at that depth. So we have equilibrium, apparently, between the tar mat and asphaltenes at higher, lesser depths, right? What's interesting is the SARA analysis that people have done for the tar mat matches our prediction of what the composition of asphaltene, aromatics, resins, and saturates should be in the tar mat. So the reason I'm showing you this is because I'm just trying to emphasize that we have a good model of the phase behavior of asphaltenes, and then that allows us to take-home ideas that we're able to describe this. And I should say we've developed a deposition tool that's now used in industry to describe deposition of asphaltenes. But this allows us then to develop a model of kerogen. So we start with our asphaltene model, and as I said, as the kerogen matures, you get more and more cross-linking. These represent cross-linkers. So we're going to take our asphaltenes and we're going to cross-link them to form a swollen gel or a cross-linked polymer type phase, where we can equate pressure and chemical potential from outside to inside this kerogen. The model we use was developed by Gabi Sadowski's group. It's based on a elasticity model due to Flory. And we can use that, and we can essentially fit the cross-linkers and the functionality in this cross-linking model, this is the elasticity model, to swelling data that's done for oil, for kerogen of different maturity. The orange here is the most mature, the blue is partially mature, and the red is immature. And here is alternatively, these are immature kerogens. You can see that there's a swelling ratio on adding different components to the kerogen. And so what we're doing is, given we choose the parameters for a kerogen, and then we predict the amount of swelling for each of these different components here and here. And what we see is that we get nice agreement. It's not perfect, but we get nice agreement for the amount of swelling for mature, partially mature, and as well as immature kerogen. And so then we use that as the model of our kerogen. Now, what's unique about this is we now have a model. Let me show here. We have a model of a kerogen, and we have nanopores within the kerogen. So instead of being graphite pores, these are permeable pores. So there's a solubility of the organic in the kerogen phase itself. And we'll set up a pore network model that looks like this. It describes now the solubility of component within the kerogen, but there's also adsorption in these nanopores. So we set up a density functional theory that describes this permeable pore. Given the permeable pore, we can then describe how different components, here these are all 6 carbon components from benzene to normal hexane, and how they will adsorb in a nanopore. The blue represents the density profile of the kerogen, so this is our kerogen surface. In here, this is the solubility of benzene in a, what is it, immature, and then a partially mature kerogen. Same thing for the for these alkyl components, methylcyclopentane, cyclohexane, and so forth. The reason we want to be able to describe this is we can then describe how an oil partitions between the nanopores of the kerogen and the kerogen matrix. This is important for understanding the amount of hydrocarbon in place in these shale formations. We can, we're assuming 15% porosity, which has been measured with the, in our laboratory with the NMR. You can see that the benzene, for example, all of these C6 components are 20% in the bulk. We're now looking at how much of that is, what the fraction is that's dissolved in the kerogen. So in the kerogen, 40% is aromatic, and then less for the alkyl components, and much less for the linear alkanes. And so there's a composite, which is the 15% porosity that is a nanopore, the rest being the kerogen, and we can see what the partitioning of a C6 components, let's say they're all 20% in the bulk, what would be their percentage in the in this composite kerogen material? So what we can then do is describe partitioning of components, like in this case, methane. This is real experimental data for methane in a, here in a mature kerogen. Here are immature or partially mature kerogen. The points are experimental data, and the curves are predictions from the density functional theory. We can also compare with molecular simulation results. In molecular simulations, people typically, when they simulate the kerogen, once they simulate an equilibrium state, they freeze the kerogen, and then they try to absorb molecules into a frozen kerogen. And that's not realistic. The kerogen is actually flexible. So we're going to perform our own molecular simulation, and within a kerogen that's flexible, what the absorption will be. But still, we see absorption of methane in a kerogen from molecular simulation. We see nice agreement for CO2 as well. This allows us to then calculate the, for example, for CO2, what the enhancement of production would be. And so we're predicting, for example, absorbed densities, as well as dissolved densities in kerogen. This is with the Eagleford shale gas. What's interesting is that what you find is carbon dioxide will preferentially move to, this is the percent of gas that's dissolved in the kerogen matrix for each component. You see that CO2 strongly prefers actually to be dissolved in the kerogen matrix compared to these alkyl components. And so this will affect our enhanced oil recovery from these components. So in summary, we've developed a new kerogen model, we've developed a new permeable pore model, and we've, as much as possible, validated the model versus molecular simulation. We've then, I didn't show, but the pore size distribution shows that most pores in these nanopores are 3 nanometers and smaller, but we'd like to do more pore size distribution analysis for shale samples, characterize the kerogen fluid interactions by looking at kerogen swelling with mixed hydrocarbons as well as supercritical carbon dioxide so that we can test the model. We're looking at kerogen water systems and then heat of adsorption. And we're planning to extend this to a higher dimensional pore model. All the work on the kerogen system was supported by the American Chemical Society through the Petroleum Research Fund or the Robert A. Welch Foundation. Work on asphaltenes has been supported by Chevron as well as Deep Star. The work on the kerogen systems was done by Jinlu Liu here. She's now with Halliburton. And the work on asphaltenes was done by Sai Panaganti, who's now with Petronas. So thank you for your attention. Be happy to answer any questions. And again, thank you.
Thank you very much, Walter, and for keeping time. We are open for questions, please. Don't be shy. If you want to ask something in Portuguese, you can do by chat and we translate for.
Hello, Professor.
Hello.
First, I would like to thank you for your talk. I would like to ask 2 different questions, if you allow me.
Sure.
The first is whether you could talk a little bit more about the associative term of the SAFT model and the computational cost. And the other would be whether you see any obstacle that make it challenging to apply DFT models to represent the complex equilibrium between hydrocarbons and other components in complex systems such as shale gas reservoirs. Thank you. One more
Okay, sure. So to answer the first question, the association model in SAFT is takes some additional computational time, and people have found whether using any of the SAFT variants, from cubic plus association to PC SAFT to SAFT gamma me. I guess are some of the more popular versions right now of SAFT. That it does take additional time to calculate the association term. It's similar within the density functional theory, although I thought it would be really dramatic, but it's not so dramatic. But does increase the amount of time. The calculations I showed can take anywhere from minutes to maybe an hour or a bit more with the density functional theory. Now your second question, I didn't quite get the first part. You wanted me to talk about the complexity of applying the density functional theory to these sorts of querogene models. Is that right?
It's about to use the FT models to study the equilibrium between mixtures in a nanopore between hydrocarbons and maybe CO2 and water in nanoscale.
So you want to know what the challenge is?
Yeah, to represent real systems, not just one single pores.
Okay, so when we develop SAFT as it developed the equation of state, you have the chain term, you have the association term. The only thing that is not within SAFT is the van der Waals attraction term, the dispersion term, and that is maybe the most empirical part of the equation of state. And so you start off with very simple terms like a van der Waals type of attraction. And so you'll see some of the early work we looked at within the density functional theory was you're using a van der Waals type of attraction. And with the equation of state for that matter. But very quickly, we developed a Barker-Henderson term for the equation of state, but other people developed their own dispersion terms. And the dispersion term that from PC SAFT has caught on as being a very popular term. Same thing within the density functional theory. Yilhim Gross's group has proposed kind of a weighted density that you can use for the dispersion term. And it seems to give very, very nice results. And so we're using that from Sauer and Gross. And that allows us to use PC SAFT in the bulk and the same parameters in the inhomogeneous system. So it's maybe movement to study some of these molecules like methane, ethane, CO2 are not necessarily so difficult. Interestingly, when we wanted to simulate carbon dioxide, the students needed to do a grand canonical Monte Carlo simulations. She needed the chemical potential for carbon dioxide. And so she went through and did a Whittem test particle insertion and other tricks to get the chemical potential for the carbon dioxide model that we were using, and wasn't able to get very good results. There was a lot of uncertainty in the chemical potential. Instead, she used PC SAFT to get the chemical potential of carbon dioxide. Using that chemical potential, she got excellent results for carbon dioxide simulation. And so it's just that carbon dioxide is a little complex because of the charge distribution in molecular simulation. But again, using the model, we're simply using the bulk equation of state parameters. And that's what we're moving to study things like micelles, inhomogeneous polymer systems as well.
Thank you, Professor. Thank you.
Sure.
I think it's Richard, no?
Yeah,
oh,
yes,
okay,
Professor Richard Gallagher. Professor Alex, you can ask your questions.
Oh, okay. So I posted them on the chat, but then I could just read them. So
Okay.
the first question was, you showed a discrepancy between the DFT and the simulation for the distributions on graphite. And I was wondering, you said it was, I didn't quite understand what your explanation was. So the trap force, you're using the trap force field for the simulations, is that right?
Yeah, we're using trap force field for the simulations. And then we're using, sorry, I'll run back here. So we're using trap force field for the simulations, and we're using, and it's a steel potential for graphite. And we're using the same external field within the density functional theory. But to model, you know, ethane or heptane, for example, in SAFT, as you know, the spheres are bonded, hard spheres are bonded tangentially. And so we're, so the spacing between groups is different from the spacing between the united atom model within a trap force field.
And the trap force field is a fused sphere. The bond length between two atoms or two sites is 0.154 nanometers instead of 0.36.
Yeah, exactly. So it's a united atom. They're fused spheres, and so some of the packing effects that we get that produce some of these peaks are going to be shifted, and so the period is a bit shifted between the density functional theory and the molecular simulations.
And then the second question was, this theory that you're demonstrating here, is that the ISAFT is still using a mean field approximation, that G of R is equal to 1?
Well, yeah, that's related to the previous question. So that's no, we're not using that mean field approximation. We're using so Sauer and Gross showed that using a weighted density approximation, they could use the PC SAFT dispersion term, and so that's what we're using.
Okay, so gotcha.
Literally in the bulk, the model reproduces PC SAFT, and for the inhomogeneous system, we're getting these sorts of results. But they were able to show that for adsorption, you get pretty nice agreement. We've published a paper recently with Kai Lagenbach, actually a series of papers with Kai Lagenbach, showing that we get good agreement for interfacial tension as well as adsorption.
Thank you.
As well as G of R. We can calculate G of R for like a Leonard-Jones fluid.
Walter, I don't know if you saw, but Johan Gross is with us.
Yes, I did see.
Ah, nice.
Yeah. So yeah, and I should say I didn't mention the Leonard-Jones version of SAFT that I originally developed, but has been developed by Lourdes Vega's group. So soft SAFT is also a popular version of SAFT. I'm sorry, I don't want to leave people out.
Who is the next? Yeah, Ingrid?
Gabriel's question first. I think Thiago will.
No, you can ask first.
Okay. So thank you, Professor, for your time and this presentation. Yeah. My question is more general. The literature has become more confident with simulated data. Yeah? So what I want to know is what's your opinion about the use of simulated data with the same confidence or even more confidence than experimental data? Maybe for confinated fluids.
Okay, so I'm trying to understand. It's a little hard to hear, but so you're saying that that in some cases we have more parameters than we have experimental data.
It's related, but I am saying like how do you feel about we become even more confident with simulated data than experimental data in some cases?
Okay.
The idea behind is we are using several times a lot of simulated data that we believe sometimes much more than real data.
Oh, I don't believe models. And I don't believe simulated data. But sometimes we're stuck in a situation where we don't have real data, so we need to get as close as possible, and simulation or theory is maybe a good way of doing that. I think we always have to be careful. There are assumptions in molecular simulation. There are assumptions in certainly the theory. I'll tell you, as an example, we've been studying water solubility in hydrocarbons, and that's because of natural gas hydrates. And at the same time that the Journal of Chemical and Engineering Data, when the first month they decided to accept molecular simulation as data, we published a paper in the Journal of Chemical Physics showing that if you use an SPCE model of water and a TRAP-E model of an alkane, the solubility of water in the alkane is off by a factor of 10. And so you can't trust that it's much worse than most models, most fitted models, right? And the reason for that is because water in an alkane, the alkane actually has charged groups. We typically ignore that because they're so weak that we don't care. But if you have a water molecule in an alkane and that water molecule is so dilute, there's no other, it can't find any charges to interact with, it can't interact with any water molecules, it's going to find the charges on the alkane and it's going to interact with the alkane. Secondly, what's ignored in theory typically and in molecular simulation is polarizability. And so as it turns out, the system's highly polarizable. I had talked to Ilya Seepman about this, and he said, absolutely, they've ignored polarizability, but they actually learned many years ago that the polarizability could be as strong or even stronger than the dispersion interaction energy. But they ignored it because it's more complicated to calculate in molecular simulation. But water interacting with an alkane is a highly polarizable interaction. If you take into account those two contributions, that increases the solubility of water in an alkane phase dramatically. And so I think you have to be careful in all of this. But yeah, and for hydrocarbons, I think the models are pretty good. But I think you always have to take it all with kind of a grain of salt. So I hope that answers your question.
Sure, it was a good answer and a good example too. Thank you.
If someone have time to go, they can ask before me. Any other questions? Yes, please, Professor Gross.
Johan Gross is speaking. Let me first thank you, Walter, for a beautiful talk. And I'd like to also thank Frederica as our host for this wonderful initiative. It lifts my spirit in times where I have too much home office. So beautiful. Now, the question, Walter, is for kerogenes. When a kerogene-rich phase forms, what's the nature of the phase? Is it an isotropic liquid? Is it a liquid crystalline phase? Is it a solid? And how do you describe it?
Yeah, that's a good question. So the kerogen phase is an amorphous phase. So I wouldn't characterize it as liquid crystalline. In some cases, people, if you had kerogen in your hand, it's going to be, it's firm, right? But it can undergo swelling. And experimentally, people make kerogen pellets, compress them very, very strongly, but as you introduce a hydrocarbon, it can swell. It's actually thought that there are grains of kerogen that are, and then there are pores between the grains of the kerogen. And so it's actually a fairly complex system. So we model it as an equilibrium phase, as a liquid phase. Maybe it'd be more appropriate to model it as a glassy phase. And that's unclear. But given the geologic time that fluids have had to move in that system, I think it's fair to model it as an equilibrium phase. And yeah, so that's the way it's modeled. And as I showed, we're modeling it as a cross-linked polymer type of phase. Yeah.
Thanks for your answer.
Yeah, and thanks for attending.
Any other questions?
Thiago, it's your time.
Okay, just another question. The last one. It's from Gabriel from our group. He's asking, Professor, last week, actually on Monday, we were discussing your paper that modeled micelle with SAFT. Do you think that DFT is capable to deal with this kind of system accurately?
I think it is. What we're doing there in that paper, we've modeled micelle formation and inverse micelle formation. We're now modeling partitioning of components into the micelle. We'll be comparing with experimental data from Professor Irina Smirnova's group from Technical University of Hamburg, and we believe that, yeah, we can describe partitioning of components. We'll be able to describe, we haven't done this yet, partitioning of, say, alcohols into the micelle. They can actually substitute in for surfactants within the micelle phase. In the calculations we've presented so far, we were using a mean field type dispersion term. And so we're moving to using this Sauer and Gross dispersion term within those calculations. The application we're looking at is in separations of a component between the aqueous phase and the micelle phase. I don't see any reason we can't describe those sorts of systems and do that reasonably accurately. Although when I've presented that work or talked to people about it, they are impressed that we're able to get a stable micelle at all. And it is a delicate balance, I think, of interactions. So so the hope is that as we understand the phase behavior more, that we'll be able to describe, say, a wider range of those sorts of systems. But we've been doing that both with surfactants as well as block copolymers. And it's also led to systems like we're studying bottle brush polymers and dendrimers and other things where we can describe partitioning of solvent as well as solute. So, but we're at the beginning stages of doing many of these calculations.
Great.
Thank
you very much.
Can I ask?
Yes. Sure. Anything.
Walter, talking about gain potential, during the calculation, you may be trapped in a local minimum, sorry, especially for confined fluids. How you usually deal with this problem?
Okay, so I didn't quite get. How do
Sorry.
we deal with the chemical potential, or how do we?
Well, no, the gain potential.
Yeah.
Doing the calculation can give you a local minimum, not a global minimum, especially in confined fluids.
Right.
So how you usually deal with this problem?
Yeah. Then you're right. That's a challenging problem. And you know, I guess there has been some work, and we essentially try different starting configurations, and to try to identify the different structures that could be present, and what by looking at the free energy, determining the equilibrium phase. There was years ago, I gave a talk on some of the density functional theory work to at Notre Dame, and Mark Stoddard was there. And Mark Stoddard essentially asked me the same question, because he has done research in just that sort of area of trying to identify all the metastable states, and so you can identify the most stable state. So we don't have a methodology that we're using to identify all the various states of the system and try to identify the stable states. When we look at absorption, we certainly get the hysteresis, where you get the pore filling, and then pore emptying. So there's a hysteresis between the two, and we have to calculate the true thermodynamic transition in that case. I'm sure you know that experimentally, people also see a hysteresis.
Yeah, but this is only show us that you have more than one answer for the minimum. So it's a local minimum.
Right. Yeah. So,
but it does not guarantee that your dense distribution inside the pore gives you the minimum, or the global minimum.
That's right. Do you have a good solution?
Not.
Oh, okay. Well, let me know.
We are thinking about this, but
maybe Joachim has thought about it.
Sure, you can come.
Well, what I have good experience with is using how's it called? Transition path. No, what's it called? Oh, I'm missing the word. A biasing method that, Frederica, you also know, and it connects all the states from low density to high. And if you go through all the densities, then of course you essentially know what the lowest free energy is, because you can use histogram reweighting to find out.
Yes, interesting.
Yeah, so that works well for porous materials and adsorption phenomenon. That's what we used.
Yeah. So just to give you an example, just a quick story. When I was in graduate school, some of the early work on density functional theory in Keith Gubbins' group was going on. And they had developed some results, and they were presenting it and publishing. And it was Jeremy Walton was the postdoc, and he came to realize that the calculations were all metastable. And so we were having a group meeting, and Jeremy was explaining, yeah, so we did the calculations this way, and the results, and these were the results we got. And Keith was, as normal, just kind of half paying attention. And then he says, but now we found that really the calculations should have been done this way, and then these are the correct results. And so for you know, so we shouldn't have presented this, but this is really what we should be presenting. And I noticed Keith was just sort of half paying attention and saying, And so I said, so Jeremy, so you're saying the results were metastable and therefore they were wrong. And Keith said, what? And I realized, wait a minute, what? I should pay attention. So anyway, sorry. But yeah, sounds like an interesting approach. I want to learn more.
Yeah, with your turn.
Transition matrix sampling is what we use. That's the word I was looking for.
Ah, okay.
Okay. Transition matrix sampling. Yeah.
Yeah. Thank you.
So let's finish.
Yes, I think the discussion was excellent.
Thank you, Professor Chapman, for being with us, for the great presentation and inspiring all this discussion. Thank you very much.
Great. Thank you all for having me visit.
Thank you.
Uh,
Be safe.